So today we're going to talk about the five resonance patterns. We're going to talk about the five resonance patterns. So, starting off with the allylic carbocation. The allylic carbocation is saying, well, first we define what the vinylic and allylic positions are. So the vinylic positions are what make up the double bond. Oof, jeez. Trying to focus a camera really does do a thing. Anyways, so in saying this, we then say that the allylic position, or an allylic carbocation, if I draw something like this, we'll make it a little bit longer. So we see that there is the positive charge directly adjacent to the pi bond. Because of this, what this means is that there's one hydrogen here, there's one hydrogen here, but this one also only has one hydrogen, whereas the other CH2 groups, or the other ones in the middle, have two hydrogens, and the ones on the end have three hydrogens. So, this pi bond is going to be able to move over to this other carbon, because all three of these are a little bit hydrogen deficient. So when that happens, we're going to get three, 5, 7, 8. 3, 5, 7, 8. So when this moves over, the positive charge goes back to this carbon. You note that this carbon in the middle always has the double bond on it. It's kind of like a swivel or a windshield wiper. This positive charge, however, can move back between these places. And since both of these structures exist, it's called a resonance pattern. Okay, so in pausing on that and then coming back and saying, well, what are these other five resonance patterns? Well, we have the allylic carbocation. There's going to be the allylic lone pair, the lone pair adjacent to a positive charge, pi bond between two atoms of different electronegativity, and the conjugated pi system. So, in saying that, I'm saying that these all exist. And these are different examples of each respective category. Sorry. So, starting off with the allylic lone pair. Similar to the allylic carbocation, when we're talking about these charges, we're talking still about how many electrons are present. So that positive charge is saying that this carbon is like one electron short. It would get an electron from hydrogen, but because it doesn't have two hydrogens, it's missing an electron. This negative charge is saying that this carbon has an extra electron. So maybe a hydrogen or a proton got abstracted, taking the H itself, but not taking the electron that goes with that hydrogen. And so it was able to create a carbanion rather than a carbocation. So in this example, what will happen is the lone pair will move towards the pi bond to make a new bond between the carbon that it's connected to, or between the carbon that the lone pair is resting on, and the carbon that it's connected to. This can happen, but carbon cannot have 5 bonds. So this bond here has to then move to this carbon, and it can only move to this carbon because, again, this carbon is deficient. It's only got 1 hydrogen versus this one, which has 3 hydrogens, or this one, which has like 2 hydrogens, and thus would have no room for, more electrons. So you will see 2 arrows in this to make Jeez, my counting sometimes blows me. It's this. And since these both exist, these are resonance structure. Now, really quick, I'm going to draw the other 3 resonance structures for this. Do you think that you can figure out what they are? Pause and draw these, and then draw the other resonance. Pause and show what you have. So did you get this? In this one, where we have the lone pair adjacent to a positive charge, the positive charge is on this carbon, and when we move the electrons over, oxygen can have 3 bonds, but it doesn't particularly like it. It will then have the positive charge on that oxygen, and it'll have a positive formal charge. That is the first thing that I can say at this moment for working. In this one, where we have the pi bond between 2 atoms of different electronegativity, we will have the oxygen, which is more electronegative than carbon. This can also be said for something like nitrogen, or I won't say fluorine because fluorine can't make enough bonds to have a pi bond here, but we will specifically see a lot with oxygen. So, because this is more electronegative, it's pulling electrons, and it will pull the electrons of the pi bond even. So, another structure that can be made is the electrons from this pi bond just going completely to that oxygen. And rather than having a partial negative and a partial positive in this structure, it will have a full negative charge here and a full positive charge here, because now this carbon only has 1 hydrogen to connect it, or to fill its octet. It is not fully filled, and so it has a positive charge. And then in the conjugated pi system, we will see a conjugated pi system is whenever we have pi bonds that are separated by at least 1 sigma bond. This is a conjugated system, but a conjugated pi system enclosed in a ring is more of the structure that we will say as a resonance pattern, and it will look like this. Because all of these positions have only 1 hydrogen, all of them can exist with the pi bonds at that location. And this is why you can also see a benzene ring drawn as a circle in the middle of it, because technically all of these bonds are neither fully single or double bonds. They are a hybrid between. They have a bond strength of like 1.5. And so these are the 5 resonance patterns. And let me know if you have any additional questions or need any additional clarification.